I'll begin. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray to be with us today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so I think I'm going to use the projector here for a minute, if it'll let me. Partly because I may have given you... no, I want to start presenting media. Come on. Is good? Let's see if it'll let me turn off the lights this time. See, this thing has become like all the other ones. Did it? Nah, it's just messing with me. Oh well, I guess we'll have the lights on. Okay, so we are talking about the matrix exponential today to start with. If I don't yammer on too long about this, we'll get to the non-homogeneous systems. Hopefully that'll happen today. So my goal for today is the matrix exponential and variation of parameters for systems. Anyway, so here was the matrix exponential. Basically, you take the power series from calculus 2 for the exponential as inspiration and replace the real variable with a matrix. And it turns out that makes sense. I mean, it has to be a square matrix, right? The square of a square matrix is still a square matrix. The cube of a square matrix is still... Anyway, so it's the sum of square matrices, which is, again, a square matrix. And this series happens to converge for all possible matrices. Now, I proved a couple of things for you guys last time. We noticed that the exponential of the zero matrix was the identity, right? Now, I did this a slightly different way, but here's an explicit calculation. E to the a times e to the minus a, if you multiply these out, just collect like terms like the identity, and then to first order, this is just distributing. You get I, a minus a plus 1/2 a squared. So all these higher order terms are canceling, and you're just left with the I. So e to the minus a is the inverse, multiplicative inverse of e to the a. This algebra I'm doing here is allowed. It doesn't matter how you group it, because we can actually prove that the matrix exponential not only converges, but converges absolutely, which allows you to rearrange sums however you like without changing the outcome. In contrast to the dreaded conditionally convergent series. Anyway, so basically here's the deal. The inverse of a matrix exponential is just e to the minus whatever the input was. Now that means it's an invertible matrix, right? That means the determinant of e to the a is non-zero. And that also means that the columns, oh, I'm sorry, not a, this should be e to the a. The columns of e to the a are linearly independent. That's true even when a is not that kind of matrix, right? Like 0 is not a matrix with linearly independent columns. 0, 0, 0, 0, 0 is far from linearly independent. It's like the worst, right? And yet e to the 0 is I, which is like the best. So the exponential of the matrix is pretty nice. Anyway, so here's another calculation I wanted to show you before I put this thing away. And I will put it away pretty soon here. So if we calculate e to the a plus b, just kind of a different way to look at the calculation. I was going through at the end of class last time. But e to the a plus b is I plus ab plus 1/2 ab squared, right? Which is I plus ab plus 1/2 a squared, ab, ba plus b squared, when you multiply that out. On the other hand, if you just multiply e to the a times e to the b, to second order you get I plus a plus b, 1/2 a squared plus 2ab plus b squared. All right. We got that out of our system last time, right? So anyway, the point is here, if you take the difference of these two guys, right? E to the a plus b minus e to the a plus b, you see the difference. What happens when you calculate the difference to second order? You've got these guys canceling, right? The a squareds cancel, the b squareds cancel, and you get ab plus ba minus 2ab. In other words, wait a minute. Oh, I'm subtracting the top one from the bottom one, so it's the other way around. I get, 1/2 of 2ab minus that, which is 1/2 AB minus BA. This thing is important. It's called the commutator of A and B. It has fundamental importance to quantum mechanics. All right, so maybe you guys will study quantum mechanics when you take our course in quantum mechanics here. Let's see here. Or maybe when you go on to another school, you'll study quantum mechanics. I don't know. I'm doing an independent study which involves some quantum mechanics this semester with some students. I can't say I'm doing it justice, but I'm trying. So anyway, this is just, again, the second order contribution to this correction to the law of exponents. This is the start of the Baker-Campbell-Hausdorff formula, which, again, we don't need for in here. I just wanted to mention this is a way I could derive it a little bit more cleanly. Also, here's the actual proof. In the case that A and B commute, you can prove the binomial formula. So here's a proof of the binomial formula for things that commute in all stupid inductive glory. I mean, I prove here the binomial theorem for when A and B commute. And then once you know that, you can use that to rewrite e to the a plus b in this way, and then that gives you this formula, which then follows that e to the a times e to the b is e to the a plus b. But this assumes that A and B commute, but otherwise it's pretty much like straightforward. This is Math 200 stuff, so I wouldn't hold you guys to that, okay? It's not. It's like, you know, it's for math majors, not for you guys so much. I just want you to know that, at this point I'll put it away. I just want you to know that e to the a times e to the b is not e to the a plus b generally. You got to be careful. It is e to the a plus e to the b, e to the a plus b rather, but only in this very, very special case that A and B commute. So let me just write that down once more for the record. Come on. Yes, I want to stop presenting media. Thank you. Oh, look at this. It's even a mess under it today. See, usually he just writes to the side of these things, but it must have been a very lively discussion this morning. I wonder what diseases they've cured or diagnosed today. Well, we should either be cured of Hillary or of Trump next week, so there's that. I mean, there's a silver lining here. At least one of them should be more out of the public eye after this next Tuesday, right? I think that's a plus.
Well, they'll probably talk about it for a week or so.
Oh, I know. And Obama's already reveling in the fact that he's just going to stay in, I'm just going to stay in Washington, D.C., which my girl's got to grow up. You know, I got to line my pockets like the Clintons did. Or whatever, I don't know. Him and his retired dad shtick, if you've seen him on the news shows, it's hilarious. Let's see here. So, again, matrix exponential. All I've really told you so far is its definition, right? And that if AB is equal to BA, then e to the a times e to the b is equal to e to the a plus b. But if AB is not equal to BA, it's complicated, all right? See the Baker-Campbell-Hausdorff formula. This marker's done. Sorry. At least I didn't hit you. Okay, so let's see here. So that's the basics. We got our basics in here. Check this out. So consider for a constant matrix. So let's consider a real n by n matrix. Okay, constant matrix. We can consider the following mapping. The mapping T maps to E to the TA, all right? This is a new kind of function, all right? Let me put it in words. This is a matrix valued function of a real variable. So we've looked at vector valued function, right? Now I'm saying let's look at this matrix valued function. I showed you the calculus of these a lecture or two ago, right? So let's work on the calculus of this. So what is d dt of e to the ta? All right, so what would you guys prefer more? Would you like me to show you the proof in the sigma notation, or would you prefer to see it in the dot 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 notation? What makes more sense to you guys? You like dot dot dot, all right. I think in my notes I have it for the sigma notation, but you could go either way. I think for beginning students, I think the dot 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 is not a bad thing, but you got to remember that sometimes we gotta, we gotta go back to the summation notation, the sigma notation. Now here I'm doing something stupid. There's something I'm using here, a property of scalar multiplication. So in order to do this, right, I'm thinking e to the b is equal to I plus b plus 1/2 b squared plus 1/3 factorial b cubed plus 1/4 factorial b to the 4th plus dot 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 dot, where what? Where b is t times a, right? And if you work it out, b to the power n, it's equal to, I'm sorry, I'm missing my what? T, no, sorry. Yeah, that is what I want. I'm sorry, I'll get with it in a second here. So b to the power n is t to the n, a to the n as it happens. Because t is just a scalar, so it just multiplies along. So when I'm taking the power of a matrix, the t to the n just pulls out like that, right? Okay. You guys with me so far? And then basically term by term calculus still makes sense. So when you differentiate this series, you just differentiate term by term. The derivative of the identity matrix is 0 because it's just a matrix of ones and zeros. There's no time dependence. This gives me a. Then I get plus 2t over 2 a squared. And then I get plus 3t squared over 3 factorial a cubed plus 4t cubed over 4 factorial a to the 4th and so forth. Right? And so what happens? You've got a plus t a squared. What's 3 over 3 factorial? Yeah, 2 factorial. So that's 1/2 factorial, or 2 if you like. T squared a cubed. What's 4/4 factorial? Well, that's 1/3 factorial. 1/3 factorial t cubed a to the 4th and so forth. So I think we've got a pattern here, right? You can peel out, and you can go either to the right or to the left, whatever floats your boat. I'm going to pull it out to the left, but you could just as well have pulled the a out to the right. But if I pull it out to the left, I've got a plus I plus ta plus 1/2 t squared, 2 factorial rather. I mean, it doesn't matter. 2 is 2 factorial. 1/2 factorial t squared a squared plus 1/3 factorial t cubed a cubed plus dot 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 dot. Close parenthesis. What do you got? Well, yeah, this is exactly what? Yeah, e to the ta. Right. So, in other words, we have a e to the ta. So there's a beautiful identity that we have just found. The derivative with respect to time of the matrix exponential to the ta power is equal to a e to the ta. Any questions? Yep.
A is a constant matrix.
Yeah, right, a is a constant.
So we don't have to worry about product rule for matrices.
Right, yeah, I mean, if a was not a constant matrix, then Well, that would be a problem for advanced calculus. There's a lot more nuance in that problem. But yeah. Okay, so what next? So what is the, why are we investigating this whole thing? It's because we are trying to solve, just remember what our goal is. What's our goal? Our goal is to solve dx dt, right, equals to ax for constant n by n matrix A with real entries, right? See, this is so annoying. Why did I say all that when I could have just said A is an element of our n by n? I mean, you know? Oh well. I already said it though. That's our goal, right? Do you guys remember what a solution matrix is? So I would remind you that if we have the derivative of a matrix with respect to time is equal to A times said matrix, then this makes it a solution matrix. Is a solution matrix. Let me just go through that again briefly. Basically, if you've got d dt of these column vectors, x1, x2, xn glued together, right, is equal to A times the concatenation of these column vectors. And then these column vectors we should think of as vectors of functions, if you like. All right. So suppose that the matrix X, this n by n square matrix of functions, satisfies the equation dx dt equals to ax. That then means that the columns are all solutions to the differential equation. Let's see why. So this is this equation right here, right, is exactly that, right? These are interchangeable. But then properties of the derivative, I mean, how we differentiate component-wise, which means that you could think of it as differentiating column-wise. And then, so this is how we differentiate a matrix. We differentiate it component-wise. Again, that means that I'm differentiating each column separately, if you look at it at the level of column notation. And then over here, by the concatenation proposition, which would seem to be sort of a rather specific bit of linear algebra for me to get into. The reason I get into that specific and not entirely well-known bit of linear algebra, matrix theory really, in our first discussion, is precisely because it's so important to this discussion right here. I mean, it's that concatenation proposition, that fact that when you multiply a matrix times a bunch of columns glued together, it's the same as multiplying that matrix on each column separately and gluing those together. This is an identity of matrix multiplication. And it's so important because what that means then is that this one matrix equation gives us n column equations. And they're exactly the ones we're interested in, because we've got dx dt equal to this. The first columns have to match up. The second columns have to match up. The nth columns have to match up. Right? So I get n solutions. Each column, right? Each column in the solution matrix X is separately a solution to our problem. So, observation. I think you'll need to pan over a bit. X equals to e to the ta is a solution matrix. So, why is that? Right? Because we have dx dt is d dt of what? e to the ta in this case, which is a e to the ta, which, by the way, is ax. So what does that mean? So let me just, moreover, e to the ta is invertible. Therefore, its columns are linearly independent. So not only do we have a solution matrix, we have what's called a fundamental solution matrix, right? In other words, theorem e to the ta is a fundamental solution matrix for dx dt equals to ax. And if you remember our theory, that means that the general solution, x equals to e to the ta times a constant vector, is the general solution to the problem. Yay. So we just solved an arbitrary, completely arbitrary system of n first order differential equations, homogeneous differential equations for arbitrary constant matrix. It's just e to the at times a constant vector. To be like, you should ask yourself the question, so why did we spend 2 days with all this eigenvector stuff then, right? Like, if this is a general solution, why don't we just use this? What's the rub? What's the catch? Yeah, this is everything. I mean, in the case that, even in the case that you need complex solutions, e to the ta's got it in there somehow. Yeah, I think the rub is, how do you actually calculate e to the ta, though? What is e to the ta? It's a power series of matrices, right? So that means you have to calculate the matrix for the system to an arbitrarily high power and take the sum of such things. That's generally pretty hard. But there are some things that help you. You know, helping hands, let's say. There's something called the Kayla-Hamilton theorem. Say, like, what does the Kayla-Hamilton theorem say? It says that if, suppose the determinant of, a minus lambda I worked out to, like, whatever, lambda squared minus 3 lambda plus 4, all right? If that is that, then the Kayla-Hamilton theorem says that a squared minus 3a plus 4i is equal to 0. This is what the Kayla-Hamilton theorem says. Whatever the characteristic polynomial is for your matrix, if you plug the matrix into the characteristic polynomial, it works. That's the Kayla-Hamilton theorem. So this is really nice because if you have that, then you can take the power series for the matrix, right? And you can eliminate squared powers for this. I mean, you can simplify the power series using this. It's still kind of beastly. So one is the Kayla-Hamilton theorem. That's sometimes helpful. Two, if a to the if a to the k is equal to 0, and for some k, then e to the ta is equal to what? I plus ta plus 1/2 t squared a squared, 1 over k minus 1 factorial t to the k minus 1, a to the k minus 1. And that's just that's a finite calculation. So if it happens to be that the matrix powers to 0 at some point, then you can just calculate the matrix exponential by a finite sum. There are matrices like that. These are called nilpotent matrices. Let me see if I can find you one. What's that? Yeah, I don't know. Let's see here. For example, this is kind of a lazy example, but here it is. 0, 0, 0, 1, 2, 1. I mean, it's kind of a dumb example because I could solve the differential equations it corresponds to really simply, but just for the sake of being brief. This, what's a squared? If I give an interesting example, it'll eat a bunch of our time, is my point. So let's keep it relatively simple here. So this squared is what? Let's see here. One, right? Anything else left? Well, you guys confirm or deny? Yeah. What's a cubed? It's just 0. All right. So this is a so-called this matrix is nilpotent order 3, as it happens. So I can actually calculate e to the ta for this directly. It's I plus t times a plus 1/2 t squared a squared, right? And then 0. It's all 0 past that point out. So this infinite series truncates, and you can actually calculate it. This is 1, 1, 1 plus what? Plus t times 0, 1, 2, 0, 0, 1, 0, 0, 0 plus 1/2 t squared 0, 0, 1, 0, 0, 0, 0, 0, 0, like that. And so put it all together, what do we got? We got 1, 0, 0. And the second column, we've got t, 1 from this one, nothing from that one, 0. The third column is more interesting. Third column, we've got ourselves a 2t plus 1/2 t squared. And we've got a t from here, and that's it. So what we've just worked out for the matrix exponential tells us we can solve dx dt equals to ax has general solution x of t equals to c1 times 1, 0, 0 plus c2 times t1, 0 plus c3 times 2t plus 1/2 t squared, t and 0. And there you go. The only thing here that the last 2 lectures gave us access to was what? The first piece, right? That's the only eigen solution here. So apparently the eigenvalue is 0, and it's repeated 3 times for this matrix. You can actually see that from the original matrix, because if a matrix is either upper or lower triangular, then a theorem from linear algebra says that the numbers on the diagonal are the eigenvalues. So like 0, 0, 0, those are the eigenvalues. And it so happens that the geometric multiplicity here is 1, and the algebraic multiplicity is 3. But we don't have to go through all that, because we just calculated the matrix exponential directly. All right. This problem, though, is very special. All right. It is, in fact, generally the case that you can write a matrix in terms of what's called a nilpotent piece, and a diagonal piece. Any matrix can be written as the sum. There's a theorem, right, that says that A is equal to D plus N. So this is a diagonalizable piece. And this is a nilpotent piece, right? In fact, these commute, so like D times N is equal to N times D. That's part of the theorem. And so you can calculate the matrix exponential in terms of this decomposition in kind of a nice way. But I don't know, I never teach that in here because it really requires a much longer discussion of linear algebra. I'm just mentioning it for your informational purposes. So let me show you what we do in here, because we need some method to calculate the matrix exponential, right? Like we're spoiled. We've got this tool which has all of the solutions we ever need for this system, right? But now we need a way to get at those solutions pragmatically for problems. So any questions about this before I erase it? Because so there's really, this is the, like, in terms of direct calculation of the matrix exponential, pretty much to make that a decent, reasonable question for you guys, either I have to give you like a nilpotent example or something that has like a really nice pattern. Another one that you can calculate explicitly without too much trouble is I won't go through, I'll probably make this a homework for you guys because I think it's a good homework for you to do. So this is likely to be one of your homework problems. If you have J equals to 0, minus 1, 1, 0, then if you calculate E to the J times, well, let's say theta J. So theta is just a real variable, it's playing the role T did. Then what you get is you get cosine theta times the identity matrix plus J times, well, plus sine theta times J. So that one you can actually also do, because when you calculate J is just like the imaginary number. J squared is minus, like, basically the point here is that J squared is equal to minus 1, 0, 0, minus 1, and J cubed is minus J, and J to the fourth is, well, it's the identity again. And so there's this fourplicity, and you can take all of the, the even terms and group them together, all the odd terms, group them together, and the coefficients in the matrix exponential will create sines and cosines times these matrices. I think I may have done your homework problem for you, but still, it'll take you tens of minutes to think through that for yourself, But anyway, there's another matrix exponential you can explicitly calculate. And so this J, right, by the way, J has lambda equal to plus or minus I as it happens. So this matrix exponential is also picking up for us systems which have complex eigenvalues. It's in there somehow. Although there doesn't seem to be anything particularly complex about the matrix exponential, is there? And yet it's in there. Okay, so without further ado, because I'm about to run out of time, probably, if I had to, yeah. The magic formula. This seems rather appropriate, given the impending release of Doctor Strange. So, friend Paul is very psyched. He's like, finally, this isn't magic, which is just some sort of like, alien technology that hasn't been explained. No, this is genuine comic book magic in its full glory or something. I'm like, okay, Paul. Not all of us read the comic books like you do. So like, I'm not as versed in the Doctor Strange and so forth, but apparently real comic book magic. So something to look forward to. Oh yeah, magic formula. So let's work it out. So here we go. E to the TA is equal to, this is going to be one of those adding zero kind of deals. This is E to the t, well, first of all, I can trade, e to the ta minus lambda it plus lambda it. All right. So that is equal to e to the lambda it times e to the a minus lambda I times t, because lambda it commutes with ta minus lambda it, which is, by the way, equal to t times a minus lambda I. All right? Yep. It's a multiple of the identity matrix. The identity matrix commutes with everything. So if I take a number multiplied by the identity matrix, still commuting. Fair question? Now, see, this, Luke, is what you worked out a special case of this for some reason last class. I guess you were just playing. But this, you can calculate, is really the identity matrix times e to the lambda t. Now, I've traded, I'll probably make this a homework exercise. That's a good homework for you guys to do. Homework, it may be in my notes, but homework, show e to the lambda it is equal to I times e to the lambda t. Here you have matrix exponential. Here you have plane exponential. All right, so two-dimensional version of this. So like e to the lambda t, what I'm saying is that that's equal to I times, well, excuse me, that's equal to 1, 0, 0, 1 times e to the lambda t. Which, of course, is really just what? So this is an identity for the matrix exponential. The matrix exponential of a diagonal matrix is the matrix whose diagonal are the exponential of the diagonal. Or e to the lambda it is I times e to the lambda t. Okay. Now this is a beautiful thing. This we can expand. This is I plus t times a minus lambda I. T, oops, there's only one t here, plus 1/2 t squared a minus lambda I squared 1 over 3 factorial t cubed a minus lambda I cubed plus dot 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 dot. And that, my friends, is the magic formula. Now, you're probably underwhelmed at this point because you're like, doesn't seem overly magical. All right, but there it is. I call this the magic formula because this is where the magic happens. Now, let me show you what I mean. So what we need is a particular kind of vector. Well, there's a particular kind of vector we've already played with, right? Eigenvectors. What happens when we use eigenvectors? Consider. If lambda is an eigenvalue, then there exists u not equal to 0, such that what? A minus lambda I times u is equal to 0, right? Question: if a minus lambda I times u is equal to 0, what does that say about a minus lambda I squared? Like if I multiply both sides here by a minus lambda I get 0, right? So if a minus lambda I, if this matrix kills, if it annihilates the eigenvector u, right? then so does any higher power of the matrix. I can erase that too and just as well put an n there, or k, or whatever you like, all right? For any k larger than 1. So what happens then with the magic formula? What's the deal with the magic formula? When you hit the magic formula on an eigenvector, or let's say when you feed an eigenvector to the magic formula, what happens? E to the at times u, right, is equal to, and we can dispense with this stupid, we don't need to write this here, right? We can just say e to the lambda t, right? That's an identity matrix, so we don't really need to write that there. We can just do scalar scalar multiplication of e to the lambda t times this sum of matrices times this vector. So I get I u plus t times a minus lambda I times u. So when you take this identity and act on an eigenvector, that means I can just act on this acts on u, that acts on u, and I take a sum of those things, right? Basically distribution. But what's the deal with an eigenvector? This by construction is what? 0, right? It's an eigenvector. So what's left? Just that, right? So e to the ta times the eigenvector u is equal to e to the lambda t times u. This is our beloved eigensolution. So to recover the solutions we already know from our previous technique, we just take the matrix exponential, multiply it by eigenvectors, and out pop the eigensolutions. All right. Now, fine. So let me just kind of say it a different way. Our goal really is not to calculate the matrix exponential, although we can. Our goal is to find solutions to the differential equation, right? So what if we don't calculate the matrix exponential, but we still have a way of finding solutions? See, that's all we need, really, right? So maybe this gives you some inspiration. What if we could find a vector, right? So that a minus lambda I to the power k was equal to 0, but a minus lambda I to the k minus 1 vector, is not equal to 0. This, by definition, guys, such a thing is here, a vector which the kth power of a minus lambda I sends the vector to 0, but the k minus 1 doesn't. This is called this makes u not equal to 0 with this is called generalized eigenvector. It's generalized eigenvector of order k with eigenvalue lambda. So let me give you an example. So these things are really best left to be put in chains, let's say. So the way the chain works, something like this. If I have a minus lambda I times u2, all right, equals to u1, and if I have a minus lambda I times u1 equals to 0. So this makes u1 what? Plain old eigenvector, right? And this right here is what I call the chain condition. Not just me, but anyway. It may or may not be in your book. I forget what's in your book actually here. I've grown past your book as I've thought about these things. But anyway, so that's the chain condition. Why is that good? Is because if you calculate a minus lambda I times a minus lambda I, u2, you get a minus lambda I times u1. But what's a minus lambda I times u1? That's 0, right? So what do we got? We've got a minus lambda I squared times u2 equals to 0. In other words, and you also know by construction that a minus lambda I u2 is equal to u1, which is not equal to 0, right? So it goes, the second power of a minus lambda I kills the vector. The first power does not. That makes u2 a generalized eigenvector with order 2. So this is the next thing up in the story we're telling. What happens when you hit the matrix exponential? In particular, what happens when you hit the magic formula? All right, with a generalized eigenvector of order 2. What happens then? Consider. So we take e to the ta, right? And we act on u2, where u2 is as above. So first of all, we write the magic formula. Now, the cool thing about the magic formula, guys, is that while I'm writing it for the eigenvalue, I didn't assume in the derivation of the magic formula that lambda was an eigenvalue, right? This calculation makes sense whether lambda is real or complex. Whether lambda is an eigenvalue or not, that's a true equation. It's just only for eigenvalues do you have a way of actually simplifying this series when you act on it by a vector. When it's an eigenvalue, then you get these generalized eigenvectors and eigenvectors which make this series truncate when you multiply it on the vector. Like, check out how this works here. So this is u2, t squared over 2, a minus lambda I squared times u2, and then stuff. So what happens this time? This time, this quadratic piece goes to 0, right? And so does all this. Everything higher also vanishes, truncates, right? So even though the matrix exponential doesn't generally truncate, except for very special cases like a nilpotent matrix, when we find these very special vectors called generalized eigenvectors, and when we arrange them in chains like this, then the calculation of the matrix exponential is not only manageable, it's pretty simple. So this gives me e to the ta times u2 equals to e to the lambda t. This is u2. And what's this? By construction, by the chain condition, that's u1, right? And there you go. This is yet another solution that we can find, solution type we can find for the matrix exponential. Now, whether or not there actually is a solution of that form in the matrix exponential depends on what the nature of the matrix A is. All right, like if A is diagonalizable, you can't find this kind of solution in there. Because if A is diagonalizable, it doesn't have a generalized eigenvector of order 2. It has a complete set of eigenvectors, so all you get is eigensolutions. But there's a theorem in linear algebra that says any matrix has a Jordan basis. And a Jordan basis is a set of vectors which are arranged in chains like this. And so basically you can find that basis, and then once you have that basis, you can just hit the matrix exponential, and out pops the solutions. And you know that there are n solutions there because the matrix exponential is a fundamental solution matrix. And this is actually how you can calculate the solutions. You just have to calculate the Jordan basis for a matrix, which is not an easy thing, but that is a method. All right? I mean, this is a hard problem. We're talking about completely arbitrary systems of first-order differential equations of arbitrary order, right? This allows for complex, so how does the complex story work here? If lambda is a complex eigenvalue, this is giving us a complex solution. it's a linear homogeneous problem, that sum of a complex solution contains a real and imaginary solution still makes sense, and we just pick off the real and imaginary part of each generalized eigenvector solution, and those give us two separate real solutions. Let me try to show you some from the projector if it's, well, I'm going to let you guys catch up, but. Okay, so the thing I will test you on in class, right? So in terms of explicit numerical ones, mostly like 2x2 problems with numbers, you have to work it out, find the eigenvalue, blah, 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 blah. So really you just have to understand this in terms of explicit calculations up to second order. Okay, I'll try to give you a homework problem where you actually face it explicitly. But I also want you to be able to do symbolic problems here where you don't actually have an explicit matrix, but I give you data. Like I say, okay, this is a 4x4 matrix. You have these vectors, u1, u2, u3, u4, they're related in a certain way. All right? I want you to understand how to use that data paired with the magic formula to construct solutions. So I really do want you to understand what we did today. But I wouldn't actually expect you to calculate a Jordan basis for a numerical matrix 3x3, 4x4, 5x5. That's way too hard for the linear algebra in here. But if I give you the Jordan basis, you ought to be able to put together what we've done here to work problems. And so I'll give you homeworks which give you a chance to understand that for yourself before the test, right? So, any questions? I know it may sound scary right now, but trust me, students have done these in the past. They're not that bad once you get the hang of them. But yeah.
Can you just repeat once again the definition of Jordan basis, please? Or maybe that.
A Jordan basis is a basis of generalized eigenvectors. Never trust me until I plug this thing in. This media center's got an attitude, I tell you. Come on. Display is currently turning on. Please allow a few moments for the process to complete. So the Jordan basis is a little bit more than that, though. Not only are the generalized eigenvectors, they're arranged in chains. So they have to be connected by that chain condition. If you had three of them, you make the third one go to the second one. You make the second one go to the first one. So it makes the third one a generalized eigenvector order 3, the second one order 2, the first one order 1. Generalized eigenvectors order 1 are just eigenvectors. So anyway, here's the type definition, 5.54. So like here, let me see if I can find something a little bit more explicit. So these matrices are actually in Jordan form. So like matrix A has eigenvalues 2, 2, and 2, and 3, and 3. I can tell from looking at this matrix that there are 2 eigenvectors, and there actually will be 3 generalized eigenvectors. In fact, in this one, you can calculate a minus 2i times e2. E2 is just my notation for 0, 1, 0, 0, 0. It's the standard basis vector, right? So if you take a minus 2i times e2, that gives you actually the second column. Well, when you subtract the 2i, it removes the 2 down the middle, right? So like, if you can visualize a minus 2i in your mind, it's a matrix which has in the second column 1, 0, 0, 0, 0. So that's the second column of this matrix. And if you calculate a minus 2i times e3, it's e2. All right. And so this condition and that condition make E1 and E4 eigenvectors, but E5 and E2 are generalized eigenvectors of order 2. and E3 happens to be a generalized eigenvector of order 3. I was hoping I would do more of that. I guess that's all. I just to give you explicit. I wanted to give an explicit example here. So here's the sort of symbolic problem I'm talking about. Suppose you have an eigenvector U1, generalized eigenvector U2, generalized eigenvector U3. See, these all have eigenvalues 2, right? So you can show that a minus 2i squared on U2 is 0, and a minus 2i on U3 cubed is 0. So to find the solutions then from the matrix exponential, first I get this, which that's analogous to what I did to start with here, right? So like when you multiply an eigenvector times the matrix exponential, you just get back the eigensolution that we already did before. X2 produces e to the 2t times ut plus tu1. And then the generalized eigenvector order 3, when you multiply it times the magic formula with eigenvalue 2, with lambda equal 2 put in there, I get I times u3. I get t a minus 2i times u3, but this is equal to u2, right? This a minus 2i squared u3, the first copy of a minus 2i brings it down to u2. And then the second copy brings the u2 back down to u1. So what you get is e to the 2t u3 plus tu2 plus t squared over 2 u1. And this is how we generate things like t and t squared in solutions. We couldn't get those from the eigenvector technique, right? They were just exponentials, sines, and cosines. There were no like polynomials. So like the polynomials in solutions are coming from generalized eigenvectors, actually. In retrospect, here's another answer to why there was a t in the repeated root solution. It's because some matrices have generalized eigenvectors. Those give rise to the t in the solution to the matrix exponential. That's actually my favorite answer as to why there's a t in the repeated root solution. But, yeah. So the general solution to this problem is that. So you see, you can work this problem without actually having a numerical matrix is the point. Giving you a specific numerical matrix and making you find the Jordan basis, that would be an unreasonable question. Yeah.
How did you get to U1 click on the last part?
Oh. This one? So U1 is an eigenvector. That's given here, right? A minus.
I just mean in the very last calculation where you had the A minus.
Yeah. Oh, yeah, I'm sorry. Yeah, sure. So a perfectly legitimate question. A minus 2i squared, where was I? U3. So that's a minus 2i times a minus 2i times u3, right? So this is a u2. So the first application gives you U2, and then it's U1. Yeah. So that's the beauty of the chain is not only does it. Oh, right. But that's how it goes. Now every once in a while I mess with students and I like change the numbering so that my chain actually has like 2, 1, 3, just to see if people are thinking. And not just trying to memorize the end result. I've done that. Will I do it this semester? I don't know. I'm thinking that I should spend less effort trying to trick students. Here is a good example of an explicit numerical one I might ask you to do. So here we have 3, 1, minus 4, minus 1. You calculate the eigenvalue, you get 1 repeated. You go looking for eigenvectors, you just find the 1. So we need to find then a generalized eigenvector of order 2 by solving this equation. All right? So I do that, and it gives me something like this. In this case, I can put u equals